Hi, let's go ahead and continue with section 4.3, exponential functions and applications. Before we begin, let's talk about exponents for a bit. So to jog your memory on exponents, we know from our exponent rules that, well, in particularly negative exponents, we always want our exponents to be positive, but it may be written as a negative. So your rule is if I have a number raised to a negative exponent, to make the exponent positive, we change it in position. So it'd be 1 over a to the n power. Now the reason why it's 1 over is we're essentially moving it. So think of that a, since a whole number, as over 1. So we're taking it from the numerator's place and changing it to the denominator to make it positive. Similarly would be if we had, for example, 1 over a to the negative n. To make it positive, I would write it as a to positive n over 1, which would just be a to the n. So let's do an example with numbers. What if I have 3 raised to negative 2 power? Well, if I want to make that exponent positive, I would write it in the denominator's place. So it'd be 1 over 3 squared. And 3 squared means 3 times 3, so 1 over 9. What about we had fractions? What if we had an example like, say, 2/3 squared raised to negative 2 power? Alright, in such case, this negative 2 exponent, because it's in parentheses, applies to each one separately. So it'd be 2 negative 2 power over, or the denominator of 3 with a negative exponent of 2. Or we can do, to make this exponent positive, is flip your fraction. So you have 3 over 2. And that makes your exponent positive. So that would give us 9 over 4. Each number would be squared. Alright, so that's a quick review on how to deal with negative exponents. Let's continue with our section. In this section, we're going to work with objective 1, draw the graph of an exponential function. 2, understand the exponential function with the base e. 3, perform calculations involving exponential expressions. And 4, applications involving exponential functions. Graph of exponential functions. As the name implies, exponential functions involve exponents. However, unlike quadratic functions, which have a variable with the exponent of 2, or polynomial functions, which have the variables with exponent 3 or 4 or higher, or even rational functions, which can be expressed using negative exponents, exponential functions differ from all the functions we have studied in this course so far, and the variable is now the exponent. That's what makes it different. Definition. A function in the form f of x equals b to the x power, where b is greater than 0 and b is not equal to 1, is called an exponential function with base b. So just to emphasize, greater than 0 means it's not negative and it's also not 0, right? So it's any number that's bigger than 0. So a half, 1, 2, that's fair game. And not equal to 1, well, it just can't equal to 1 because 1 raised to any exponent will just give us back 1. Now let's talk about what we just did here. There are 2 requirements on the base of the exponential function. First, we must have b not equal 1 because, as we said, 1 raised to any exponent will always give us back 1. 2, we must have b greater than 0 or positive to avoid non-real complex function values. When an exponential function is evaluated at certain values such as x equals negative 1/2. Let's start our discussion on the graph's exponential functions with the simplest exponential function, f of x equals 2 raised to the x power. Without knowing much about the function, f of x equals 2 to the x power, yet we'll evaluate the function for several x values. All right, so this is our first exponential function. Let's go ahead and use a chart so we can just see what we'll get. Let's go ahead and make a list of negative values and make a list of positive values. All right, so this is going to be our x value. We're going to replace x with the numbers we chose to be x. So we chose the number 0, -1, -2, and -3. All right, 2 to the 0 power. Any number raised to the 0 power is always 1. That's a rule. A number raised to the 0 power will give us 1. The only exception is 0 to the 0 power, but you'll talk more about that in future classes, so don't worry about that. All right, negative exponents. 2 raised to -1 power. All right, so that just gives us back 1/2. 2 raised to -2 power, we rewrite it to write in the denominator's place. So we get 1 over 2 squared, which gives us 1/4. And then we have 2 raised to the 3rd power. So we change our exponent to the bottom to make it positive. And 2 times 2 times 2 gives us 8. So we have 1 over 8. So we just added some lists of points. We have the point 0, 1, -1, 1/2, -2 and 1/4, and -3 and 1/8. So these are points that'll be part of our function. Now let's continue our list. Let's write some positive numbers. All right, we have that 2 to the 0 power is 1, which we already did. 2 to the 1st power is just itself. 2 squared, 2 times 2 gives us 4. 2 cubed, 2 times 2 times 2 gives us 8. And if you don't know any of these or you're not familiar with them, use your calculator. There's no shame in that. It's very helpful. So we now added some more points. We have the point 0, 1, 1, 2, 2, 4, and 3, 8. All right, let's go ahead and plot them and see what figure we have. The two charts display the traits of every exponential graph, a graph that is essentially determined by the left and right hand behavior. The first chart displays the behavior of f of x on the left, while the second chart displays the right side behavior. Plotting these points, we should notice the following. So here are our points. We see that on the left-hand side, they're getting smaller and smaller and smaller fractions, right? And this is because a negative exponent just changes it so we have a fraction, where the denominator gets bigger and bigger, making a smaller number. So we see it gets smaller and smaller and smaller and smaller, but no way will we ever get a negative. And on the right side, we see numbers get big super fast. So in summary, the left side, we see that as x approaches negative infinity, the points we found for f of x equals x squared are getting closer and closer to 0 without reaching 0. As our discussion of rational functions, we call the line y equals 0, which is the x-axis, a horizontal asymptote. The right side. Unlike rational functions, horizontal functions only control one end of the graph. We see that as x approaches infinity, the points we found for f of x equals x, 2 to the x power are increasing, taking away from the horizontal asymptote. There are traits that every exponential graph will possess. One end will flatten out towards the horizontal asymptote, while the other will take off away from the horizontal asymptote while ever changing directions. For this reason, drawing the graph of even more complicated exponential functions can be accomplished with simple two-step process. First, find your horizontal asymptote, y equals a number, and 2, plot 2 points. That's all you need. We need 2 points, and that will give us an idea what's going to happen. Because we know that one side's going to flatten out, the other one's going to take off. So this would be our two options. That weird L-shaped figure. Or actually, it can also go this way or that way. Let's consider the following four exponential functions. So this will be part of our next set of examples. We will revisit our chapter 1 discussion regarding the graphing of g of x equals a times x minus h squared plus k as a transformation of f of x equals x squared to help. So recall your transformations. Do you remember what happened and how a parabola changed based on the h, the k, the a, and if there's a negative? While all function transformations kind of follow the same idea, but they're applied slightly differently. So let's see how exponential functions differ. All right, insight onto how we determine the location of a horizontal asymptote for exponential graphs. For f of x equals a times x minus h squared plus k, h would be the shift left to right, a would be the stretch or compression of the graph and possibly reflect across the x-axis, and k would shift the graph up or down. Starting with f of x equals b of x, that has a horizontal asymptote of y equals 0, and considering that g of x equals a times b with the exponent of x minus h plus k, h would be the horizontal asymptote on the x-axis. I think they mean k. K would shift the horizontal axis left or right, leaving the horizontal. No, that's right. I just don't like that wording of a horizontal asymptote. H shifts your graph left or right. A would stretch or compress and possibly reflect across the x-axis, leaving the horizontal asymptote at the x-axis. All right, the only value in g of x that would change the horizontal asymptote would be k, shifting the horizontal asymptote up or down. So your horizontal asymptote will always be y equals a number. And what number is that? It's always a number that's hanging out on the side, not in the exponent's place. So let's take a look at example 1. Determine the horizontal asymptote of each of the following functions. All right, so do we have a plus k? No, right? Since there's no shift up or down, the horizontal asymptote is the x-axis, so y equals 0. B, I have a plus 4 at the end. Since there's a shift for units, we have a horizontal asymptote at y equals 4. For C, we see our function has a minus 1 at the end. So there's a shift down to units, 1 unit. So we have a horizontal asymptote at y equals negative 1. And D, we have no number on the side that's being added or subtracted. So there's no shift up or down, and our horizontal asymptote is the x-axis, so y equals 0. Now that we know the location of each of the horizontal asymptote, we can graph the curve by finding 2 points and determine which side goes towards the asymptote and which goes away from the asymptote. All right, I'll do the first and C with you. So let's do A. Example 2, graph the following exponential functions. So A, we have f of x equals 5 with the exponent of x. So we know we have a horizontal asymptote at y equals 0. So let's plot 2 more points. But let's be careful about it. Let's pick points that would make it easy for us. Let's pick points that would make our exponent 0 or 1 or negative 1. All right, so if we just plug in 0, we get 5 to the 0 power, which gives us 1. And then if we try an exponent of 1, we get 5 in return. So we have 2 points. We have 0, 1, and we have 1, 5. So we plot them. We have our horizontal asymptote, and we have our 2 points. So we know our graph would look something like that. One side gets closer to your asymptote, and one side pulls away. Let's take a look at C. All right, so remember, our goal to make it easy on us, we're going to pick our points wisely. We want our exponent to be 0 because we know that a number raised to the 0 power will give us 1. So it'd be nice to have an easy number to work with. All right, so what numbers do we want to pick for x? Let's make x -2. -2 plus 2 gives us 0. And let's make x -1. All right, so we pick -2. We got our exponent of 0. 1/3 raised to the 0 power is 1. And then we're left with 1 minus 1, which is 0. So far we have the point -2, 0. One more up, we have 1/3 raised to -1 plus 2 power minus 1, which gives us 1/3 raised to the 1 power minus 1, which is 1/3 minus 1, which is -2/3. So just to emphasize, you want to get a common denominator, and then you can subtract. That's how they got -2/3. So we have the point -1 and -2/3. All right, so we have our horizontal asymptote, which we stated already in our last example. We have a horizontal asymptote at y equals -1. So one point will go closer to your asymptote and the other will pull away. So that's how we can use only 2 points. Moving forward. Natural exponential function. Well, before I move forward, not to scare you here, we have pi, right, which is about 3.14, but it's also a button on your calculator. So don't break your brain over this problem, just use the button. Use your calculator for this problem. Moving forward, natural exponential function. In this section, we have discussed exponential functions with bases of 2, 5, 1/3, and even pi. All numbers that satisfy the requirement of b being greater than 0 and not equaling 1. For our next topic, we will introduce the irrational number e as the base of our exponential function, often referred to as a natural exponential function. So just like we have pi, which is the famous irrational number, now we add e to our list. It's about 2.7. Just as pi is an irrational number that can be approximated as 3.14, e is a non-terminating, non-repeating decimal that can be approximated as 2.7. When one studies calculus, the number e is derived from the expression the limit as n approaches infinity of 1 plus 1 over x raised to the n. For the purposes of this course, a calculator will be used to determine the expressions involving e. Example 3. Let's graph the following exponential function. To begin, what's our horizontal asymptote? We don't have a number on the side, right? So we have a horizontal asymptote at y equals 0. And now let's pick some more points. Let's choose the exponent to be 0 and then 1. E to the 0 power is 1, so we have the point 0, 1. And e to the first power is about 2.7, so 1, 2.7. Let's plot these points. We have our horizontal asymptote, and once we plot them, we get one that gets closer to our asymptote but never crosses, and we get one that pulls away, making our L-shaped figure. Let's take a look at B with some transformations. So we notice we have a horizontal asymptote with a 5, so I have y equals 5 for a horizontal asymptote. Now let's pick 2 more points to plot our graph. All right, let's let x equal -3 and one more bigger, so x equals -2. We chose to work with -3 because we see that -3 plus 3 will give us 0 for the exponent. E to the 0 power will give us 1, so that we have here -1 times -2 times 1 plus 5, which gives us 3. So I have the point -3, comma 3. If we choose 2, let's make sure we have a calculator for this one. We'll get here 1, so that we get e to the first power, and we punch this into our calculator. E times -2 equals plus 5. So we get -0.4. And then we plot our points. And just like before, one point gets closer to our horizontal asymptote but never crosses, and the other point pulls away. Calculations involving exponential expressions. When working with e in example 3, we use the approximation of 2.718. For our continued use of e and for evaluating most exponential functions, we will use calculators. When studying exponential functions and using a calculator, 2 buttons become useful. So this varies from calculator to calculator. So you'll have a button that looks like something like these, and that might be your exponent button. You also have this on your calculator functions on your phone. If you turn it to the side, you get access to more buttons and thus more types of functions to work with. So just to make sure you're on the right track, try punching these values into your calculator, and you should get that answer in return. If not, figure out which way to punch it in. For some numbers, calculators, you have to work on the order that you punch things in. Same thing for E. You don't want to type in 2.7 blah 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 every time. Your calculator has a button for E. Look at your calculator and see what button it is. And just to make sure you can punch in these values and get the appropriate answer. If you can't find your calculator and how to do these, you can always YouTube your calculator and maybe how to type in E. I mean, there's so much on YouTube already on how to punch things into your calculator. Feel free to take a look. Moving forward, exponential applications. Whether calculated and added to a savings account or charged because of carried balance on a credit card interest is the most common example of an application involving exponential functions. Consider $4,000 at 6% annual interest invested for 3 years, but with the interest calculated and paid monthly for 36 months. All right, so let's start with month 1. Month 1, we have a formula P times R times T, where P is our principal, our starting amount, and R is our rate, which is your percent in decimal form, and T is time. All right, so we have 4,000 at 6% compounded monthly for 36 months. So we get $20 interest. So what's our balance so far? 4,000 plus 20, you get 4020. All right, month 2. We have a new starting amount of 4,020 times our interest and our time. We get $20.10 that will be added to our amount above. So now we get 40.10. And we do this for every month, and we have to do this 36 times to figure out our amount after 36 months. That's a lot of work. Considering the first 3 calculations, we see the monthly interest started at $20 and it's slightly increasing each month. Over the entire 36 months, the total interest when paid monthly will be greater than the simple interest calculator of $720. How do we find the total interest over 36 months when interest is paid monthly, usually described as compounded monthly without going 36 separate calculations? Which we don't want to do 36 separate calculations, right? Well, there's a formula. In general, the formula for calculating the account balance of P dollars at an annual interest rate R, compounded N times at a year for T years, is this. That's your formula. It's usually called your compound interest formula. Compound interest. All right, so just to emphasize what these letters mean, A is your amount, your ending amount. P is your starting amount, which is called your principal. R is your rate, so it's the percent you're given. N is how many times it's compounded. So if you have words like monthly, that would be compounded 12 times. Quarterly would be 4 times. You can have semi-annually, weekly, daily. Those are words you'll see, but monthly and quarterly are probably the most common ones. All right, let's do example 1. Calculate the ending balance for $4,000 at 6% compounded monthly for 3 years. All right, so let's start by filling our pieces. A is what we want to find. P is 4,000. R is 6%, which we change it to decimal form, which would be 0.06. N is 12. And T time is 3 years. Time is in years. All right, so we just go ahead and fill in all these values into our formula. And from here, don't break your head. Use your calculator to find your answer. Now, when I teach this, filling in your formula is the challenging part, but I often see that students don't practice enough getting the answer using their calculator. So take a moment, make sure you punch into your calculator. Now, if I may give you some advice, the way I enter it is I first start by punching in that fraction, getting an answer, then adding the 1, getting an answer, raising it to the exponent, in this case 36, lastly multiplying that 4,000. So try that order. All right, I trust you can do example 2. Very similar. Anytime that interest is calculated, the higher frequency of times interest is compounded will always result in more interest, even if the difference is minimal. That being said, there is a limit to how much interest can be earned regardless of the interest compounding frequency. This leads to a second formula for calculating balance, which gives the maximum amount balance regardless of the frequency of compounding interest. The formula for compounding a balance of P dollars at an annual interest rate of R for T years compounded continuously is this one. Now, what makes this different from your other problem is this word, continuously. So it never stops calculating the percent, the interest. But there's a limit. So there is a maximum number you'll get no matter how many times you compound that interest. Let's take a look at this example. We'll do example 3. Calculate the ending balance for $4,000 at 6%, compounded continuously for 3 years. So because we know, or because we have that word continuously, this lets us know that we have to use our new formula. A equals our principal times e raised to the rate times time. So we have our principal of 4,000, and we have the exponents r times t. We multiply our exponent, and then from here, it's just calculator work. Make sure you know how to get this answer. All right, that's it for this section. You have some homework to practice. If you have any questions, you can always email me or ask your essay leader. Have a nice day.